1.4, and we're going to expand our ability to find probabilities. And in particular, what we're going to be learning is what we call the binomial probability formula. And its use is it allows us to find probabilities when not everything is behaving the same. So that's Jensen language, but it's true, right? And so we're going to have a formula that's given to you. You'll be able to bring that with you to the exam. Our job is to get ready to use it, and they're going to have that happen in a few instances. So what I did is I went through the homework, and I'll give examples that are related directly to the homework that you're going to be having. So the first thing I need to introduce you to is the binomial probability formula, and it's a little bit overwhelming at first potentially, but we don't want it to be, and so we're going to work on that. Okay, so that's typically how the formula is given in a book. C n x little p to the x q to the n minus x. And this may be the first time you're seeing some of these symbols. And so let's talk about each one. I'm going to first focus on the variables. There's a few variables here. N is going to stand for the number of trials, the number of times you're performing the experiment. X is going to be the desired amount of successes. So a success to us could be rolling a 5, something like that. And so if we're rolling a die, it could be getting a question wrong or right on an exam. And it could be developing a side effect. It could be varying things. And it'll be apparent in the question. P is the probability of success on one trial. Q is the probability of failure on one trial. And we'll give examples so these will be even more solidified. Right now I know it's a little bit shaky, but one thing I want you to recognize is that the probability of failure has to be 1 minus the probability of success, right? They got to be opposite one another. Now there's another letter in there that's not actually a variable. I'm going to move a problem that I copied down to a little bit later, and that's this CNX button. And CNX is a big formula that counts stuff. It counts the number of different rearrangements they are. Well, you know what N and X are. And what C does, C is a function that will count it and having a certain number of successes depending upon a trial. So let me start out with an example. And so we're going to do an example that they've done in the homework. We're going to flip a coin 5 times. And the question will say this: find the probability of getting exactly 2 tails. Okay, so I need that type of example for you so that we can start identifying these variables. Again, I'm going to move that question down. So if we look at this question, the number of times we're flipping the coin is n. In that case, it's 5. X would be the desired number of successes. A success is always what the question is about. So a success is tails, and I want 2 of those tails. Now what P is the probability that on an individual flip, whether that's the first one, second one, third one, fourth one, or fifth one, what's the probability that tails comes up? And the probability of tails is 1 out of 2 options, right? We can either have it land on heads or we could have it land on tails. There's no other option. And so it's 1 out of 2 options. Well, the probability of failure then would also be 1 out of 2. Okay, so this is a unique situation where the probability of success and failure are the exact same thing. And if we go use our formula will tell us the probability that we have 2 tails is C of, out of 5 flips, I want 2 to be tails. The probability that the first one is a tail, P, is 1/2, and I need that to happen twice. The probability that it's a heads or not a tail also it has a probability of 1/2, but that needs to happen 3 times, right? That's why they have this n minus x. It's better to be able to talk yourself through it. But here's that formula again. P and Q are both 1/2. If x is 2 and n is 5, then n minus 2 is the 3 that I'm coming up with. But you almost want to think about it as, hey, this is 2 tails and 3 heads with the associated probabilities in there. So the question you have might be, well, how in the world am I going to get this C of 5 2? You're going to use your calculator. So your calculator is going to have this button on it if you have a scientific one. Let me show you where mine is. So I'm going to turn on my calculator and then bring it up on the screen through the camera. So let me find it here. So here's the calculator I have. It's a $15, $10 to $15 TI-30 XISS. And if I wanted to do the C of 5 2, I would first type in the 5, right? That first thing that's there. Then on my calculator, it's here under the PRB button. See if that will focus in there. I'll come down a little bit. So I'm going to click that PRB button, and you're going to see that I have some choices. I'm going to use my arrow key to select the C, and then hit the Enter button in order to select it. And then I hit the 2 button. And when I hit Enter to see, it's going to tell me 10. There are 10 different rearrangements of heads and tails, having flipped the coin 5 times. I don't need to know that. The calculator can figure that out. But we're going to do that first. That's 10 times 1/2 squared times 1/2 to the 3rd power. And so that's what we do. We take 10, multiply it by, and I put it in parentheses. Maybe I can show that to you. Again, using this calculator. Sorry, but I think this will work out fine. 10, and then I would use the open parentheses right here, and then type in 1. Whoops, I got a negative in there. This might not be the most efficient way to do this. Let me put it up here and clear that. So I got my 10 times, and then in parentheses, 1 divided by 2, close the parentheses, and then I need to square it, times 1 divided by 2, close the parentheses, and then I'm going to raise that to the 3rd power. You can kind of get an idea of what I'm doing, and I get a nice 0.3125. That's the answer. So 0.3125 is the probability that if I flip a coin 5 times, I get exactly 2 tails. So pretty likely to happen, going to happen 31% of the time. And so sometimes the book will give you problems like this. Other times it will just give you the N, X, and P. I saw one that looked just like this. I'll have this be my second question. It said, hey, N is equal to 5, X is equal to 1, P is equal to 0.4. And then it said use the binomial probability formula to find P of 1. And so what do? C of 5, 1. P, 0.4 given to the 1 power, right? I need it to happen 1 time. The probability that it doesn't happen, if the probability of success is P, then the probability of failure, which I'll put in red, is going to be 1 minus 0.4, or 0.6, right? If I told you 40% of the people were doing something, then the people not doing it is 60%. And so that Q comes in here as 0.6, and that's got to happen the other 4 times. That's 1 success and 4 failures. How do I know I wanted 1 success? They told us when they said X was equal to 1. So now I'm going to hit 5, hit that PRB button, get my C. And if you have specific calculator questions, let me know. And what I mean by specific to your calculator. 0.4 to the first times 0.6 to the fourth. And we should come out with the probability of 1 being 0.2592 under that situation. Okay. Third example. Let me see what this one is. Yes, so that's my multiple choice. So let me do this. A die is rolled 20 times. Find the probability that there will be 10 threes. Rolled. And let me put one word in there. I'm going to put in the word exactly. Exactly 10 threes rolls. So half the rolls are threes. What's the probability of that happening? Well, let's find out. The probability that you're going to get 10 threes is equal to C. Out of the 20, I want 10 to be threes. So what do I know? I know I'm rolling a total of 20 times. I know the desired number of successes is a 10. Now a success for me is rolling a 3. A 3 is 1 out of the 6 options. So that's 1/6. I need that to happen 10 times. And Q would be 5/6. And I need that to happen the other 10 times because I need 10 to be threes and 10 not to be threes. They're not always the same number like we saw in the previous example. But we just say, hey, 20 C10. So I go get my C function, type in the 10, hit equals, and I'm looking at a very large number, so I'm just going to keep it. It's 184,000 plus. And then times, in parentheses, 1 divided by 6, close the parentheses, to the 10th, times, in parentheses, 5 divided by 6, to the 10th. And what do we get out of that? A very low probability. It has 3 upfront zeros, and then followed by a 4934. So I'll just put 493, taking out the 3 significant digits. So let's take a look at this question right here. This question comes straight from the homework, and so do these other ones, by the way. I just didn't feel a need to type them out as we could talk about them. But here we have Beth, who's taking a 10-question test, which each answer has 3 answer choices. Each question has 3 answer choices, one of which is correct. She answers by rolling a fair die and selecting the first answer only if the outcome on the die is 1 or 2. She's going to select the second one if it comes out to be 3 or 4, and she's going to select the third one if it comes out to be 5 or 6. Find the probability that she will get exactly 5 questions correct. Okay, so if we want her to get 5 questions correct, well, I need 5 questions correct. So out of the 10 questions, I need 5 to be correct. Now, what's the probability that she's going to get that first answer correct? Now, we want to think about it by the outcome that she's doing. She's selecting the probability that she gets it correct. Let's suppose it's the second one, right, for that first one. So it doesn't matter which question she's answering. To get that first one right, it's 1 out of 3 answer choices. But she is rolling this die. That die, there's 2 numbers that could come up that would be the right ones out of 6. And so it is a 1/3 probability that she gets it right. And that's happening 5 times. And a 2/3 then probability that she's going to get it wrong, also happening 5 times. So you can see that this is very similar to the question that I had just made up. So, but the probability bases are different. So I would first do 10 C5 hit enter and see the 252. So my calculator is displaying 252. Then I'm typing in times, and I use an open parenthesis, 1 divided by 3, close it. So this time I'll write out what I'm doing. To the 5th power times, open parenthesis, 2 divided by 3, close parenthesis, to the 5th power, and hit equals. And we get a nice answer. The answer is 0.1365, so I'll put 0.137 in there. That's how you do that. Now there's other questions that they're going to ask. One had something that looked like this. A company knows that there is a 58% probability that a person has a side effect when taking their drug. Okay, and then the question would be this: find the something like this. If 5 people take the drug, find the probability that at most 2 have side effects. And so they'll use the word at most and at least. In this case, they said at most. And so what we want to do is get an idea of what does it mean for at most 2 to have side effects. We have 5 people taking the drug. That means if 2 of them have a side effect out of the 5, then that's happened. Then we've met the criteria. Or at most, right? So it could be under that, 1 or even none. That's what you're going to do. You're going to find the probability that 2 develop it, 1 out of the 5, or none out of the 5. And then you're going to add those results. So out of 5, we want 2 to have side effects. The probability that somebody has a side effect is 58%. That needs to happen twice. And then the other 42% don't develop it, and we need that to happen 3 times. Or 0.58 needs to happen, I miswrote there, 1 time. So hopefully the at most makes sense. At most is that number and under. And so you'll have to do 3 separate calculations, and I just wanted you prepared for that. And it's actually shown in the book as well, and in the lecture notes that the book produces. But I also wanted to do one with you that involved a 0. Okay. And so you're going to just type these out into your calculator and just write down the responses and add them. So I'm going to first do 5, 2, whoops, I didn't select the C somehow. So 5C2 is 10, and then I'm going to hit times 0.58 to the second plus, or no, sorry, times 0.42 to the third, right? So 10 times 0.58 to the second times 0.42 to the third. And for P of 2, I'm getting 0.249. I'll just go out that far. Actually, let me just keep writing. 232032 is the full display. For C of 5,1, I'd run that times 0.58 to the first power times 0.42 to the fourth. And we're going to get something even smaller. For P of 1, we're going to get 0.090239184. And then we do need to do P of 0. which will be even smaller. So this was 5 times 0.58 to the first times 0.42 to the fourth. And then this one is going to be C of 50 is 1, is what you realize. Times 0.58 to the 0, which you may know is 1, times 0.42 to the fifth. And so if I do 0.42 to the fifth times 0.58 to the 0 times 1, I'm going to get 0.013069123. I'm going to take that number and add to that the 0.090239184. Hopefully having translated that correctly. Plus 0.249232032. And I didn't hit a 0 in there, I hit a decimal point. And so I'm getting the total of all that will be our answer, 0.3525. So I'm going to put 0.353 is the total of all of those. That would be the probability of having at most two having side effects. It's going to happen 35% of the time. And so this whole section is getting familiar with this formula, using it. They'll have good examples in the book as you look at the e-text. There's some videos out there, and hopefully this one is one in which you can glean some good information off of too. I tried to keep it really close to the home.